So this is a bit of an atypical talk in the sense that I'm going to present today on an outcome of a big data open competition that we organized at the Fritz Haber Institute in collaboration with Kaggle, where we put some computational data on the Kaggle website and try to encourage people to develop new machine learning models that best predict two key properties of transparent conducting oxides. So this is what the website looks like. This is the outcome of the competition. So I'm not sure if people are familiar with Kaggle.com, but it's the premier website for hosting big data competitions. For example, Merck was famously put their data online and had a famous competition where neural networks were shown to be superior over the previously benchmark methods, which were based on random forest. They also have hosted big data competitions for organizations like the TSA, which is the American Federal Institution. And most recently, I noticed just this week that they are hosting a competition for CERN. And CERN's award is something like $25,000 spread over the top 3 winners. Of course, as an academic institution, we couldn't afford quite as high of an award, so we had a prize of only 5,000 euros given to the top 3 winners that I listed here. This is the outcome of the competition. It ended up a few months ago already. And we had about 900 people participate in this competition, which was online for about 2 months. So it's encouraging that even though with little, relatively speaking, monetary incentive, that a lot of people were keen on trying to come up with better machine learning models. So I will discuss the 3 winners, the techniques, the models that were developed by these 3 winners. But before doing so, I want to sort of set the stage for why we care about modeling transparent conducting oxides in the first place. And so these are an important class of materials that are used in a variety of different optoelectronic devices, for example, solar cells or light-emitting diodes. So anytime you have light that needs to be absorbed, for example, in an active layer of this device, you need a transparent material that is also conducting, that we can form a device. And of course, if this material absorbed in the same range as this visible light, then that would be detrimental to the overall device efficiency. And so typically, in terms of at least solar cells and light-emitting diodes, indium oxide is one of the prototypical materials used as a TCO material. And that's because its optical band gap is about 3.7 eV, so it's sufficiently high, and leads to about 90% optical transparency in the visible range. There is some need to go beyond indium oxide based on sort of its expense and scarcity. In addition, if you were able to tune the bandgap to even higher energies, then it could open the way for new technologies, for example, in all-transparent transistors or in materials that have, so with a large bandgap, you can also have high breakdown voltages in different transistor architectures. In terms of designing materials with variation in bandgap energy, one strategy, of course, is to alloy compounds. And so in terms of indium oxide, a convenient choice is the group 3 oxides. So going up the column of the group 3 elements, from indium, which has a bandgap around 3 eV, gallium oxide has a bandgap around 5 eV, and aluminum oxide has a bandgap around 9 eV. And so if you were to successfully alloy these compounds, then in principle, that opens a large range, all the way from 3 eV to 9 eV of possibilities in terms of bandgap energies that can be tuned just based on the choice of the relative composition of indium, gallium, and aluminum. And indeed, experimentally, this is something that's been shown, at least for the ternary materials, so the mixtures of gallium and indium, and aluminum and gallium. Reports show that you can modulate the bandgap somewhere between 3.8 and 7.8 eV. And this is something that our experimental collaborators in Berlin work on, and so there's a lot of advances in terms of the growth techniques in growing these alloys with these crystalline alloys. Something that makes this problem difficult, however, is the fact that indium is most stable in its cubic phase, whereas gallium is most stable in its monoclinic phase, given by the symbol here, beta, and aluminum is most stable in its rhombohedral phase, alpha. And so if you were to alloy these materials together, it's not clear at a given composition what the stable structure will be. And so in terms of machine learning models that can approach this problem, then we have really 2 target properties. One is, of course, the bandgap energy, which is important to the optical transparency. And the other target property is the formation energy, which is an important consideration in terms of stability. And in this case, what we used was not a formal definition of the formation energy, which typically subtracts the energy of the material, the alloy, and subtracts the atomic components from the material of the alloy. Instead, what we use is this so-called relative formation energy, where we subtract off the bulk pristine compounds, the energy of the bulk pristine compounds. What this effectively does is it subtracts out the overall linear trend that you find in the formation energy as a function of atomic composition. And that linear trend, a strongly linear trend, is really easy for machine learning models to pick up on that. So in terms of errors, actually formation energies was being drowned out. By subtracting out that linear trend, we have a much more difficult problem. So in terms of the data set we put online, we computed a data set of about 3,000 compounds. 2,400 of them are these binary, ternary, and quaternary materials, so aluminum, gallium, indium oxide. That's the training set. The test set is 600 compounds. And the structures that we included were 6 different lattice types. These are the 6 lattice types that are reported in the literature to be important in terms of the lowest energy structures for the pristine materials. The unit cells range from anywhere from 10 to 80 atoms, so we included supercells intentionally to make sure that the machine learning models were size consistent. And the features that we provided were just the geometries, the structures, both for the training and test sets, the lattice vectors and angles defining the unit cell or supercell, as well as the atomic compositions of aluminum, gallium, and indium, and the space group labels of the 6 different space groups that we used. And so here you can see a distribution of the 2 target properties, so the band gap energy and the formation energy in the test and training sets. You can see that they follow a qualitatively similar trend. So we have a similar distribution between those 2 data sets. What makes this problem difficult in terms of developing machine learning models, and we heard a lot about this already in the first talk of the session, is coming up with a nice representation that can tackle materials that have large configurational disorder. And so for alloys, we're confined to a lattice. And so what that means is that, for this cartoon over here, what I'm showing is if we have a cubic lattice, for example, and at a 50-50 mixture, we have equal concentration of atom A and atom B. And there are several different ways you can decorate these different lattice sites in this unit cell. And each one of these distinct decorations is a configurational state, and that has a corresponding formation energy, for example. So what that means is you get large variations of the target property at a specific composition. So this is very difficult in terms of just obviously it's impossible to try to model this with just the atomic properties or some property that's a function of the atomic composition. So instead what you need is to be able to describe this decoration of the lattice, this local structure. And in terms of the number of states possible, for the quaternary case, so you have 3 atoms being mixed on a lattice, so that's something like 3 to the n possible, where n is the number of sites, 3 to the n possible number of configurational states. So the large variation is seen in the formation energy. It's also seen, of course, in the band gap energy, same idea. Configurational disorder is very difficult to model. And so in terms of coming up with the right machine learning model, the participants had to be able to tackle this problem sufficiently well. So I'll sort of transition and getting into the winners and what they were able to come up with. But first I want to note an important aspect of this is the fact that although we had 600 values in our test set, the way Kaggle does it is they partition that test set into what's called a public leaderboard and a private leaderboard. So the private leaderboard is what is used to evaluate the final winners, but the public leaderboard is what's online for the entire competition, so for the 2 months of it. And this allows the participants to see on the fly how well their model might be performing. But an important outcome of this is the fact that there was a significant shift in the errors that we saw associated with the public and private leaderboards. And so here I'm showing the number of participants. It's a histogram based on their average root mean square log error. So this is the metric that we used to quantify the error in their predictions, and we average it between the 2 different properties, so the band gap and the formation energy. And this is given by this equation here. So what you can see is that for the public leaderboard, only 100 values of the test set was taken for that, which is a very small subset. And as a result, what seemed to happen is a lot of the participants sort of trained their models to optimize their public leaderboard score, and that was detrimental in terms of the actual private leaderboard score. So we saw a significant reshifting of the winners when the private leaderboard was finally revealed, which is based off only 500 different structures. And indeed, the winners of this competition actually trusted more their cross-validation score, so the 5-fold, 10-fold was used typically for the winners. And so that's just a note to say that you should always trust that. If you ever want to participate in a competition, be sure to trust your metric for generalizability of your machine learning model, not necessarily the public leaderboard score. Okay, so only 4 participants were in this first bin, so that's with an average root mean square log error of 0.53. And so I'll talk about the 3 that won the competition. We already heard about SOAP this morning, and of course it's probably not a surprise that it was used in this competition. And this is submitted by Lars, who's a third-year PhD student in Imperial College London. And so what he uses SOAP, of course, which is already described earlier. So here we just have this Gaussian density distribution of the neighbors surrounding some site in a given lattice, based on within some cutoff radius. That's then expanded in a basic set of radial and spherical functions. And so this describes a local environment of a given site. So this feature vector was then inputted into a neural network, but it was averaged. What's curious about this is that it was averaged over all sites of the lattice. So one would imagine that you should probably take, since we have 3 or 4 atomic species, aluminum, gallium, indium, oxygen, you should probably take a feature vector that is representative of each one of those individual species. But in fact, one average vector of the entire system, per system, plugged into a neural network actually was the third place winning solution. So here you can see the performance of that for the formation energy and for the bandgap energy. And what's notable here is that the test score, so this is using an entire 600 value test set, not just the public, the private leaderboard. But what's notable here is that the formation energy is still, there's a much higher accuracy for the formation energy compared to the bandgap energy. And so the formation energy seems to be a property that's much better described, for example, by the local coordination environment. In terms of the second place winner, a very different strategy. So this was submitted by the Bochum group. So Yuri worked with Thomas Hammerschmidt in Thomas Hammerschmidt's group. And what they did is they came up with 7,000 derived features. So this is also similar to the first speaker of the session. So this large list of derived features based on several different categories. So geometric features, which includes, for example, bond distances or number of nearest neighbors. And then the statistical derived features based on those. So mean, standard deviation, etc. In terms of trying to capture the local coordination environment, the scalar was included here. So this is the moments of local electronic density, which is computed from a self-returning walk in the lattice. So here, this is the hopping matrix between different sites. And what's interesting here is that the orbital is inputted, because you can imagine that for this to be realistic for a system, you need to compute the orbitals of the system. And that was not the case. That's too expensive to input into a nice machine learning model. So instead, they used a approximate coupling. So they used, I think it was titanium, the orbitals from titanium, and just as a way of quantifying the coordination environment. In addition, elemental properties were included, so the electron affinity, the ionization potential, and several different features. So of a list of 7,000, they trimmed this list using importances based on these regression tree models to a subset of about 200, and then inputted that into the light gradient boosting regression tree method. And so you can see, again, the qualitatively similar trend in the sense that the formation energy is a much easier term to predict, quantity to predict than the bandgap energy. And you see significant deviations at low bandgap energies from DOT. In terms of the winning solution, this is a very clever idea that was submitted by Takanori Yamamoto, who is a CEO of a startup in Japan. And so what his insight was is that basically atoms in a crystal is similar conceptually to words in a sentence. And so what he uses is what's called the n-gram model, which is used in linguistics to predict, for example, given a sequence of words, like please turn your homework, what is the next word, what's the most likely next word to be? So you can imagine that, in this case, it's very easy for us to see it, but trying to train the model to see that might be difficult. So the way they do this is by separating this overall sentence into a series of unigrams of single words, bigrams, which is the combination of 2 nearest neighbors, and trigrams, which are a sequence of 3 words connected by a nearest neighbor that share a similar nearest neighbor. So you have these contiguous sequences of words, and then you can train this feature is then basically counted over a list of documents or some word database, and based on the probability of finding, for example, this trigram next to the word in or the, is then used to predict whether or not what the most likely next word will be. And so the same idea can be applied to materials. So here we have, of course, atoms and environments. A sequence of atoms, so in this case the unigram becomes a coordination environment, and the bigram becomes a sequence of coordination environments. So the coordination, for example, of indium in a 6-coordinate next to oxygen in a 2-coordinate environment. The trigram is just a sequence of 3 coordination environments. So what you're doing is you're converting this picture into a crystal graph now. So here you have this sequence where the nodes are the atoms, and the edges here are defined by the bonds, which is defined by the coordination environment. And in terms of the features, what this looks like is, again, just counting the number of features in the data set based on a given sequence. So counting the number of times oxygen in the 3-coordinate environment shows up, oxygen next to a gallium, in the 3-coordinate next to a gallium in a 4-coordinate shows up, etc. So you build essentially a histogram of these, and then you divide by some sort of normalizing factor to account for various sizes, so volume or number of atoms. So that was combined with the kernel ridge regression method, and he analyzed several different combinations of unigrams, bigrams, trigrams, and quadrigrams. You can see that although it did make a difference in terms of his ranking slightly, really the performance is similar across the complexity of the coordination numbers, the sequence of coordination numbers. And again, we get this consistent difference between the formation energy and the band gap energy. And with that, I'll just summarize and mention that in terms of this outcomes of this Nomad big data competition, what we found is that these 2 targeted properties of formation energy and the band gap energy, of course, are very dependent on configurations, which is what people know in terms of material science. But the broader community, which is who tends to go to Conductors.com, probably didn't know that. And yet the ones that won were these structural dependent features instead of these, of course, compositional dependent features. Coordination environment, so in the sense of these sequence of coordination numbers used with kernel ridge regression, or some sort of feature engineering, which all the local coordination environment combined with gradient boosting, or of course the SOAP combined with neural networks. And consistently, what we saw is there's about 3 times larger error for the band gap energy than the formation energy, which indicates that the formation energy is probably well described by the geometric considerations, whereas the band gap needs much more electronic information to get accurately described. So with that, I'd just like to thank you for I should thank the people who helped contribute to this. So the award committee, of course, Angelo, who's here in the audience and will present tomorrow, and Luca Girandelli, as well as the people at Kaggle, and all the co-workers at the Fritz Haber Institute, as well as the many organizations who made this possible. And I'd like to thank you for your attention. I'm happy to take any questions.
Questions? So, first of all, I think this is great. This kind of competition is fantastic, and I think will help move the field forward if we keep doing this. So I applaud this whole idea. A specific question about the actual test, though. So those of us who work in the alloy theory community have been solving problems like this for a long time with cluster expansions. So it looks like you tailor-made a project for a cluster expansion. Did anybody try that, and why didn't it win?
Well, because it's 6 different lattices. So cluster expansion, you have to build a cluster expansion model for those 6 different lattices.
I said you only had 3.
No, I had 6 lattices, and that's a good question because I worked a lot actually in cluster expansion before moving more into machine learning methods. And the problem here is one of the lattice types that we included is a spin-LT type structure, which undergoes significant relaxations. So cluster expansion then, by implicitly defining the atomic distances to be constant, loses its basis set. Right? It's a basis set over the finite distances. And because there's significant relaxation, then cluster expansion is actually not appropriate for this problem. So it works well for 3 of the lattices. So the monoclinic phase, it works well. For the XBI phase, it works well. For the helial phase, it works well. But for the other ones, there's significant relaxation, so it fails on those.
That's a quick one. I was kind of surprised that only one person used SOAP. Was there other people who used similar methods? As
No, just one person. Well, that we know of. I don't have everybody's code.
They don't have everyone's.
No, that's true. Yeah, I don't have everybody's code, but certainly the guy that used SOAP was not expecting to win because he started just a few days before. But it's such a better method than what most people have used that it turned out well for him. But I think it's because not many people on Kaggle.com who visit this, they're not from our field, right?
They're not familiar with this.
So in fact, this guy actually, the guy that won it, 3rd place, he wasn't even aware of SOAP. He had a friend who suggested it. So
Is he going to share the 1,000?
I don't know what he did with it. It's his to share.
I'm curious about this first place approach. So
Yeah.
does it really just take the connectivity of species? Is there any geometric information? Is it really just a graph of atom types?
Certainly, the coordination number is a feature here, right? So you bid it based on, so it's not just, so for example, the indium in a 6 coordinate, 5 coordinate, 4 coordinate, etc.
But it doesn't look at
Bond
distances
distances.
of,
No, yeah, so, right. So, and it's actually even more rough than that in the sense that the coordination number. We heard a nice elaborate method for dividing the coordination number already this morning or earlier. But this is just based on the Shannon radii, so some proportion of Shannon radii. So if bond distance is less than, say, 30% times the sum of the Shannon radii, this becomes, in the coordination shell. Very rough estimate even of the coordination number. And we since sort of went beyond this and used the effective coordination number. I don't think anybody's familiar with that. We just do a sum over bond distances, take the minimum and divide by that. And we can improve slightly on this. But basically, just capturing the qualitative distances or differences between the lattices based on the coordination shell seems to be sufficient. So it is surprising as well. And it probably benefits from the kernel ridge regression method helping out.
Yeah, so of course having material with a wide bandgap is very important for transition. So for transparent oxide materials. But also another very important problem right now is to find a material with P-type conductivity.
Sure.
So what if somehow taken into account in this project or what it is?
This is step 0 of that, and certainly, I mean, we do, P-type connectivity and put effective axis as the next target property and do a 3-body optimization. I mean, certainly that's probably an additional step, but and it's important. It still becomes difficult.
So the participants asked to submit documentation of their solution?
Only the winners.
Okay, so you contact them afterwards
Yeah, exactly.
and say, okay, tell us how you did.
It's very, Kaggle does a really good job of making sure that nobody was essentially cheating, reverse engineering the solution. So they have to give a presentation and they have to provide their code. It's very transparent. So we'll put all this online once we sort of finish some of this write-up and analysis. We'll put all this stuff online as well.
So just on that last point that you just said, not accusing anybody of anything, but couldn't I just generate a lot more data and train my model, do a bunch of DFT and train a bigger data
You can
set?
take the structures I provided and you can just recompute them. That's true. But the community that could do that is probably quite small. And we did this with FHI Ames, so we know in principle that's licenses. Yeah, that was certainly a concern. But we just hope that people were honest generally, and we hope that if we saw their code, we would be able to scrutinize it sufficiently and be able to tell what they were doing. But indeed, a few people, so after the competition ended, one guy posted on the discussion thread that he tried that same thing. He tried to take the structures and just re-optimize them as a way of predicting the properties. But he used the wrong package. So they got the same results. So fortunately, that didn't work out too well for him, but it's certainly a concern. And the only way we avoided that was, and this is probably more of an issue if you want to host a competition, and that is that we didn't want to give them the actual structures, right? So we didn't want to give them the optimized geometries. And so we couldn't link it to the Nomad database and say, here's all the structures you could possibly use. Instead, what we did is we actually sort of symmetrized the structures by giving them the Baker's law structures, so generated from the pristine materials, just projecting based on the linear average of the structure, essentially. And so we gave them sort of this idealized fake structure, the geometry, which on one hand introduced noise in terms of the prediction, but on the other hand, it kept people from just taking that and calculating a single point DFT estimate and submitting that. So.
I think the limited prize maybe also helped.
But still, 900 people participated.
Still, if it was 50,000, it would be very interesting.
50,000 people will never participate, I think.
50,000 euros.
Oh.
Maybe some professors might be able to.
Does Kaggle provide you with the information about the technical backgrounds of participants? Like
The winners do. Yeah.
Okay.
Yeah. So there was certainly but no, I mean, basically the winners have to give a sort of a summary of their background, etc.
Okay.
But there were a few people who, in the reshuffling, I mentioned the reshuffling of the public versus private label board, and there were a few people who did surprisingly well. So that in the public, they were really low, maybe like 60 or something. They jumped up to be fourth place, for example. One guy comes to mind. And so we were surprised by that result. So we contacted them afterwards to see sort of what their approach was. And it seems like they used high dimension and ran a neural network with it. You know, they really have a background in material science, but there's still the tools are available, and they're able to sufficiently figure it out. So
That's really cool.
yeah.
Okay, maybe it's